We talked about spontaneity, okay? And here's a reaction that's spontaneous. And we know it's spontaneous because delta G is negative, right? But it tells you nothing about the speed, right? That was one of the first comments that we made in the thermodynamics chapter. It's spontaneous, but it doesn't mean it's fast. And this reaction, here it is, all right? If you set up some hydrogen peroxide, it's not going to readily, quickly degrade into H2O and O2. But it will eventually. It's spontaneous. Okay? Now in this chapter, at the end of the chapter, we're going to learn about catalysts a little bit. Although you're probably already familiar with what a catalyst is. Anyone want to try to define what a catalyst is? So everything that you guys are saying is correct, all right? So, because activation energy, that's at the start. You have to overcome the activation energy to get things going. It's kind of like when I introduced the idea of spontaneity to you, like the burning fire, right? That's spontaneous, but once you get it going, it's spontaneous, meaning that you don't have to add any more energy to keep it going. But you still have to give it that initial kick, right? That's the activation energy. That's what you guys were talking about at the start. Now later on, I can show you in the slides, okay? But later on, you'll see that. You'll see that described with a diagram that looks like this, where you've got energy on this axis, and this is just the, again, this idea of the reaction coordinate that I showed you the other day, okay, where we go from reactants to products. And that energy, we can have any kind of energy on the scale. It could be delta G, it could be delta H, it could be whatever. Let's just consider it as energy now. We have to overcome that hump, and once we do, then we'll be able to go down the rest of the hill. And that's what that activation energy is right here. Activation energy. The energy that it takes to get to the top of that hill. And we'll be talking about what happens at the top of that hill in more detail when we get there. Coming soon to a lecture near you. But the other important thing about a catalyst is that it's not consumed during the reaction. It's there, and it speeds things up, and it speeds things up by lowering the activation energy. So with a catalyst, it speeds it up because the hill isn't so high anymore to overcome. So it's faster to get from over the hill and then down over there. But notice that the starting position and the ending position stayed the same. That's because all of our energy values, all of our thermodynamic values are state functions. And we talked about state functions the last time, right? So basically adding a catalyst, and in this case here we're adding a potato wedge that has an enzyme in it called catalase. Or you dump some magnesium oxide in there, and it really speeds it up to the point where this thing gets super hot and boils over. All right? So catalysts will speed things up. But that's what we're going to be talking about in this chapter is the rate, the kinetics. Kinetics is rate. Okay? The rate of reactions. Catalyst is just one thing that affects the rate. Here are some other things listed here. The physical states of the reactants, the concentration, the temperature, the surface area. We're going to be focusing our attention mostly on the concentration of the reactants in this chapter in our discussion. But we'll probably be touching on these other factors as well when we get a little bit deeper into the chapter. Okay? Talking a little bit about reaction rates, okay, with respect to the change in concentration over time. So, for example, take this top reaction, nitrogen plus oxygen goes to 2 moles of NO gas, right? And we can talk about how that reaction rate changes with respect to its concentration. So, for example, the rate with respect to nitrogen gas, it's going to be the change in concentration of N2 over the change in time. And I put a negative sign there because the nitrogen is going away. It's decreasing. The concentration's decreasing. And if you look at the coefficients, it's 1 to 1. So that's going to be the same as the rate that we would describe for the change in concentration of O2 over time. Now, if we want to make all of these rates equal, but do it with respect to the concentration, the increase in concentration of NO, notice that it increases twice as fast as the decrease in any of the two reactants. So the way we do that then, if we want to make these all equal, this is the same as plus, it's going to be 1/2 the concentration of the product. Right? It's twice as, makes twice as much, so if all these rates that we're describing in this way are equal, we basically take the reciprocal of the coefficient. All right, but I don't want to emphasize this too much, okay? Because really this is just setting the stage for the discussion that I do want to have with you. But this is kind of the idea. You can describe the rate of a reaction based on the changing concentration over time like this, and you can set them equal in this way, looking at the coefficients and doing the reciprocals. So we can also look at reaction rates in this way. Now here's a table of results, okay? We're looking for this reaction now, it's the same one, but now here it is all labeled out for you. And now we can actually track how the reactants are decreasing over time and the products are increasing over time. And you can even tell from this curve that the NO is increasing twice as fast as the N2 is. I mean, maybe you can tell. It's kind of hard, right? And the book goes into, we can calculate the slopes of, not the slopes, but we can calculate the difference over an interval of time. So for example, if we look early on and calculate what the rates are, you can see that we're going to get a different value than if we calculate, say, the rates from 10 seconds to 20 seconds. Things have slowed down a little bit. If we do that calculation from 0 to 5 minutes, we're going to get much faster rates. So that's an important point. The rate changes. The rate of consumption of reactants and production of products changes over time. Now, if I were to take this out further, notice that the reactants here, N2 and O2, they don't go away. It doesn't go down to 0. You can kind of get that from this line. It's not going to go down to 0. But the change is now stable. No more change in concentration. No more change in concentration. Okay? But the reaction's done. If we walked away and came back the next day, they're still going to be at those same concentrations. They haven't changed. Has the reaction stopped? Is the reaction done? Where is the reaction? What are we describing in this case? Way out here on the right.
Equilibrium.
Dynamic equilibrium. Very good. Okay? So what's slowing down here is the rate of consumption and the rate of production, okay? But when we're at dynamic equilibrium, the concentrations don't change anymore, but the reactions are still happening, okay? And to be more formal about it, all right, when we're at equilibrium, we've got a forward reaction and we have a reverse reaction. And the rates have changed for both of them, but when they're at equilibrium, the rate of the forward reaction is now equal to the rate of the reverse reaction. Again, that's foreshadowing for Chapter 14. Chapter 13, we're just going to talk about the rates now and how we can measure the rates and what useful information we can get about measuring the rates. Also on this slide, we're talking about the average rate. That's what this was. So the average between 1 and 5 seconds or the average between 10 and 20 seconds, okay? That's what the average is telling you. The instantaneous rate, that's something that you can get from the slope of the line that's tangent to this curve. Ooh, that was a lot of calculus sounding words there, wasn't it? All right. You all know what a tangent line is, right? Okay. So here's that same curve, all right? And you can see that the curve, it's not a straight line. It's not a slope, it's a curve. So we can draw a line that's tangent here, and you can calculate the slope of that line. We can draw another line that's here, calculate the slope of that line, and a third one here, okay? And the slope, all right, is decreasing, right? So the rate is decreasing, the rate of, in this case, consumption of reactants, Okay. Where is the rate the fastest? A, right? This is the fastest rate. Initially. The initial rate, okay, is the fastest. Now the instantaneous rate, that's going to be the slopes of the tangent lines. Now, why do you suppose the rate is the fastest at the beginning? Let's hear from someone else first. Think about it. What have you got at the beginning of the reaction? Let's just do A goes to B. Actually, I want you to be starting to think about things in equilibrium, even though we're not going there until later. At the start of this reaction, right, if we start with 100% A, which is really what this example is doing. Why is the rate the fastest?
Start of a reaction is where the concentrations of...
So concentration argument, yes. A is the highest. We have the highest concentration of A, and as time progresses, the concentration of A is decreasing. So that's right. So it's fastest because, one, we have the highest concentration of A. There's another reason, though, too. It's mostly one, but there's another reason that comes into play, too. Because what happens after a little bit of time passes? We made some B, but this is a reversible reaction. And once we've made some B, there's a rate of B going back into A. Okay? So we also now have reverse reaction can now produce A again. So, but never as much that you get 100%. So it really is this first explanation. Whether or not there is a reverse reaction happening, the concentration of A is always the highest at the very beginning. Okay? And that's why we're going to be looking at the initial rates of our concentrations when we do these experiments. The symbol that we use, so obviously brackets, you should know. Brackets means what? Concentration, which is in molarity, moles per liter. Okay? Not parentheses, but the brackets. That's specifically what those brackets are used for. We also use a sub-zero. That's the initial. It's time zero. Okay? So you'll be seeing that a lot in the examples that we use. The concentration is the highest at the beginning of the experiment. And as we deplete reactants, we have fewer reactants. So there's just a collision probability. In fact, this is called collision theory. Although, really, it makes sense, right? Have a theory about something that just seems like it makes sense to me. The more molecules you have, the greater chance they have of colliding. And as we'll see, for a reaction to actually take place, things have to not only collide, but they have to collide with enough energy, because as we talked about in lab yesterday, you've got to break bonds before you can remake new bonds. So it takes energy to do that. So the two reactant molecules, or maybe three or maybe four, they have to collide with the right amount of energy, and they have to collide in the right orientation in order for a productive collision to turn into products. We'll be looking at that as well. Okay? We need the probability of productive collisions. We're going to call that A. It's called the frequency factor. All right. Temperature plays a role as well, because the hotter things are, The more energy, the more thermal energy you have in a system, the more kinetic energy the molecules are going to have. So when they do collide, they have more energy, right? So obviously temperature plays a role. Activation energy plays a role. We're going to be discussing all of those things. So I've got a little simulation here. Let's see if it'll work. This one's kind of a funky one. So here's a reaction. We've got two green balls are going to meet to give us a diatomic molecule. That's the reaction. Okay? And let's put, you can't see it because the label's on there, but there's four molecules there. Okay? And I'm going to hit go, and we're going to see on the right how long it takes for the reaction to be complete. So let's see. Get your stopwatches ready. Come on. There we go. All right. So two already collided. We're waiting for the other two to collide. Remember, they have to they have to collide in the right orientation with the right amount of energy. Oh, they just swapped partners. You're waiting here for a while. It's like Pong. Oh, you guys are too young to remember Pong. Boop, boop. Here we go. Come on. Ah! All right. Oh, they just switched partners again. Oh, come on. All right, it's taken a while. I think you get the point, right? Why don't we increase? Oh, yeah! Okay, we did it. All right. So let's stop that. Stop it. Let's start with 10. Now, what do you think? Are we going to complete this more faster or slower? Faster, right? It's collision theory. Well, let's see. Get your stopwatches out. Let's see how fast we can do it now. Why they're more energetic now, I'm not exactly sure. Come on, we're getting there.
This is so Valentine's Day.
We're almost there. They'll find each other. There. Okay, we're done. All right, that was faster. Let's see. What do you think?
In the matter of seconds.
We're climbing the pool.
Faster or slower?
Really fast.
Yeah, let's see. Here we go.
We're just gonna pretend that they're at a bar and they're all in open relationships.
And
Missing.
not yet. Come on, guys, find each other. Ah, there we go. Okay. All right. I think you get the idea. It's a cute little simulation, right? All right. So that kind of sets you up.
Nintendo Switches.
Now you all have this slide. There's nothing written on it. Okay. You've got a blue curve, a green curve, and a red curve. And think about what is shown on this graph. Now you don't know what reaction order is yet, all right? So we're not going to worry about that. But just take a look at this and think and discuss a little bit. What do you think is happening, all right? And which ones are reactants, which ones are products, and what do you think the stoichiometry of the reaction might be? Here, let's use A, B, and C. Let's say blue is A. So let's label this one A, and we'll label green as B, and we're labeled the red one as C. What do you think is happening here? What is this describing?
I'm describing different reactions that are occurring at the same time. They're actually
All right, let's see what you guys came up with. So what do you think are the reactants here, A, B, or C? A and B, right? And how do you know? Because over time, their concentrations are going away. So here, I'm just going to stick with one color now. Otherwise, I'm going to be switching back and forth like crazy. So let's put this in. A plus B is going to C, and good. So you can recognize that from the curve. Now, what about the stoichiometry? With the molar ratio, is it 1-to-1? Is it 1 mole of A plus 1 mole of B goes to 1 mole of C? Or is it something else? Something else. Do you know what the something else is? Why isn't it 1-to-1-to-1 though? What would you expect this to look like if it was 1-to-1-to-1?
You would expect A and B to basically be the same line.
That's right. You would expect A and B to be in the same line, just like it is here. Notice on this one, 1 mole of N2 reacts with 1 mole of O2 to give you 2 moles of NO. So look, the curve, the blue curve of reactants, it's the same for both of them. So it's clearly not 1-to-1. What else can you say about this, though? C and A are 1-to-1. Why?
They're mirrored.
They're like mirrored. If I were to trace these two, if you flip C, you get A. Can you see that? So A is decreasing with the same kinetics that C is increasing. Even though those changes, remember, it's fastest at the very, very beginning at time 0, and even though they're slowing down, the consumption and production are slowing down, they're doing it at the same, just reverse rates. It says, guesses, 2A plus 1B goes to 2C, and why is that? Because B, yeah, that seems reasonable. You're right. So you're both thinking about this the right way. That's good. It's just a little exercise to kind of get your brain in the mode of what we're talking about here. Now, once again, if I extend time even further, the way these curves are going, they're all going to be about the same. Not the same as each other, but they will stop changing. That's what happens when we're at equilibrium. Okay? At equilibrium, though, this is just something to keep in mind. Even though the changes in concentration have flattened out, so they're no longer changing, the rate of the forward reaction and the rate of the reverse reaction are still there. They're just now equal to each other. So you're making products just as quickly as the products are turning back into reactants. And so it looks like things are static, but in fact, it's a dynamic equilibrium. All right, so let's now go to a practical example, okay? Here's one of those photochemical smog reactions. And this one is balanced. They should all be balanced, I hope. It's 1-to-1 to 1-to-1, okay? And just looking at that, all right, if we double the rate of nitrogen dioxide, what do you suppose will happen to the rate? Looking at this equation. So if this is 1-to-1 to 1, if we double this, what's going to happen to the rate? And we're just you can measure the rate as the production of the products. You can do it as the reduction of the reactants. Either way, let's just talk empirically now about the rate. Will the rate double? What happens if we double the rate? What happens to the rate if we double the concentration of carbon monoxide? Same thing, right? There's no difference. Okay. Now, I can tell you, right? Here's some data. Let's take a look at it. If we look at this data, there's 3 experiments, and just look at experiment 1 and experiment 2. We're keeping the concentration of NO2 the same, all right, but we're doubling the concentration of CO. Now, you all said that if you double the concentration, it should double the rate. But look what happened to the rate here. The initial rate. Is it changing?
Yep.
No. So we increased the concentration of CO, and nothing happened to the rate. So you're wrong. Look what happens here. If we look at just 2 versus 3, all right. When we look at 2 versus 3, now we're keeping CO concentration constant, and now we're doubling the concentration of NO2. What happens to the rate when we doubled NO2? Can you tell by that? It went up by 4-fold. Okay? Imagine. Now, that doesn't mean that you were wrong, okay? What it means is that just by looking at the stoichiometry, just looking at the coefficients, you can't tell what effect the concentration is going to have on the rate. You have to do the experiment. All right? That's the lesson. But the converse of that, I think it's the converse. From doing the experiment, you can actually learn a lot about what the molecular mechanism is actually having here. So I want to leave you with those 2 statements. So 1, you cannot predict effect of concentration on the rate without doing the experiment. And two, from the experiment, we can learn a lot about the molecular mechanism of the reaction. What I mean by molecular mechanism is, now think about that simulation that we used. You might imagine, when you guessed 2x and 2x for everything, that one molecule of NO2 has to collide with one molecule of CO, and when that happens, right, the bonds, are broken and reformed to give you 1 mole each of the products. Now that's one very reasonable hypothesis of how this mechanism works. And as you'll learn, the data will tell us whether that proposed mechanism is right or not. Right? If that proposed mechanism was right, then this data would have doubled the way you expected it to. It didn't. That just means that it's not that simple mechanism. Something else must be happening. And we'll be discovering what that something else is later on, okay? And how we can use this data to basically ask, is our proposed mechanism right or wrong? Because at molecular level, we don't really know what's happening. This is the first time in Gen Chem that you're now able to ask questions about how do these molecules actually collide with each other and in what proportions to give us the products. We can test those hypotheses with real data like this. And that's probably a new concept to most of you. And you know how to deal with this, right? We've been dealing with this for a semester and a half now. But this does not tell you on the molecular level what's actually happening for this reaction to proceed. Which molecules are bumping into which other ones? With what energy? With what orientation? In what combination? Is it just that one molecule of NO2 bumps into one molecule of CO and then that does the reaction? Or does something else happen? And that's one of the main underlying themes of this chapter. The first theme is understand what rates are and how to deal with them. But then how we use that to actually inform us what the molecular mechanism is. We're going to come back to that at the end of the chapter, because that's a really useful thing that understanding rates allows you to do. And the bottom line of all of this is that we've got to actually do the experiment. So let's do some formal definitions here of what we're going to be talking about. We're going to talk about reaction orders, rate laws, and molecular mechanisms. So I've already told you what a molecular mechanism is, right? We're going to derive a rate law that describes the rate of the reaction, and it has certain components to it. Now, these bullet points up here, I've already talked about them, okay? That's one that I just highlighted, right? That sums up the conversation we just had. So I'm not going to read that one again. And then this sums up the other thing that I just said. You got to do the experiment to know. And really, doing that experiment, it's a way to test the hypothesis of what the mechanism is. So when we do all this, okay, we derive what's called a rate law, which is an equation that describes the dependency of the reaction rate based on the concentration of the reactants. We don't really follow the production of products. All we need to follow is the disappearance of reactants, and we need to just follow the rate of the reaction as it's dependent on how we change the concentration of the reactants. We don't care about the products because we're doing it at initial concentrations. So when you first start an experiment initially, there are no products, okay? So part of the rate law, it has certain parts, right? It has reaction order and it has a rate constant. So let me just show you what these different things are. I'll come back and tell you what reaction order is in a moment. Reaction constant, right? This is just a proportionality constant. It's going to be a bit of a mystery to you now, but we'll talk about it in more detail later on. This proportionality constant, this relates to the molecules have to have the right kinetic energy, and they have to collide in the right proportions and in the right conformations for it to be a productive reaction. All right, so how can I put this into words. These are several factors that that include things like orientation, collision frequency, activation energy, if you remember that. Okay, this is all coming soon to a lecture near you. But we're going to start using it now, all right? And so when we derive a rate law, okay, the rate law looks like this. We're going to say the rate of a reaction, and the rate, by the way, is always measured in molarity per second. By the way, sometimes you'll see that as molarity times second inverse. You should get used to seeing units written this way as well. It's the same thing.
Is it molarity?
Molarity. Capital M is molarity. Moles per liter. And remember, molarity, that's what's in the brackets. M, molarity, which is moles per liter. And I guess if we're emphasizing how to write that, it's moles times liter inverse. All the same thing. Okay? Am I going too fast? All right, so the rate law is going to be equal to, or the rate is going to be equal to this K, this proportionality constant, multiplied by the concentration of the reactants. So let's just say reactant A, and it's going to be raised to some power, let's call that M, times the concentration of another reactant, let's call it B, raised to some power, N. Concentration, and these superscripts, this is the reaction order. So let me be specific here. M is the reaction order with respect to A, and N is the reaction order with respect to B. So if I haven't used it before, RxN, that's reaction, WRT, right, with respect to, okay? I'm just defining this stuff for you. You'll see what this means as we go through some examples, okay? But these are the components of our rate law. It's dependent on the concentration of the reactants, but in a way that reflects how they collide with each other and the overall, what we call kinetics. And the overall, so that's the individual reaction order. We can talk about what the reaction order is with respect to A separately, with respect to B separately, or we can talk about what the reaction order is for the overall reaction. This is just going to be the sum of the exponents. So in this case, it would be M plus N. And it does get complicated. We're going to keep it nice and simple in this class. We're only going to be considering 3 cases. What we call first order kinetics, second order kinetics, and zero order kinetics. Okay, now what's important about these reaction orders is there is no way for you to tell what they are just by looking at the balanced equation. To get these require, you have to do the experiment. These need to be experimentally determined. Let's put a nice big fuchsia exclamation point here. Okay? So those are your definitions. Now let's put them into practice. So this is exactly what we looked at before, the same reaction and the same data. All right. So let's just take a look at that now a little bit more closely. And I'm going to take you through this step by step. This is how you would approach the problem on your own. I blew through this the last time, so let's now do it again as if we're approaching this for the very first time. So what you want to look at, we've got three experiments here. Here's the reaction. We only care about what's happening to the reactants, okay? And we want to do a controlled experiment so that we only change one variable at a time. In doing so, we can infer a lot by that. So you want to look for two experiments where only one thing is changing and everything else is constant. Now, don't look at initial rate. This is the result, okay? So we want to see how we change concentrations. So we want to look for a case where, for example, the NO2 concentration is held constant and we change the CO. And we have that. If we just look at experiments 1 and 2, we see that this is the same. So NO2 concentration is held constant. So if we don't change that, and all we do is change the CO concentration, initial concentration, that's what the sub-zero is, look what we're doing. In this case, between experiments 2 and 1, it's changing by twofold. We're doubling the CO concentration. Okay? So this doubles. When that doubles, what happens to the rate? It didn't change. Okay? Now, let's put this into words, what we're doing here. Okay? So, when NO2 concentration is constant, if we double the CO concentration, the rate is unchanged. That's what we learned from experiments 1 and 2. So if I were to now use this new rate law stuff, right? If we were to describe the order of the reaction just with respect to CO, we would say that the reaction concentration of CO raised to the 0. This is a 0 order with respect to carbon monoxide concentration. With respect to CO concentration. In other words, if it's 0 order, that means the reaction rate is completely independent of whatever the concentration of CO that you started with. Completely independent. Now, how can that be, you may ask? We'll get there later on in this chapter, probably later in this week. We'll see when we get there, okay? We will address the why and the how. Right now, we're just learning this stuff, okay? Now, let's do the same thing for what's the reaction order with respect to nitrogen dioxide. The carbon monoxide concentration is constant. Well, let's find that first. Let's do that one in blue. So that's going to be these two. So if we compare experiments 2 and 3, we find that here this is constant, all right? CO concentration is constant. So what happens to the, sorry, not what happens. What are we doing? How are we changing the NO2 concentration when we're holding CO concentration constant? That's doubling as well, okay? It doesn't always double. You've got to look at it. If it's not doubling, you just use your calculator. You can figure out what it is. So now we can write, if we double the NO2 concentration, what happens to the rate?
Increases.
It increases by how much? Fourfold. So now the rate increases by fourfold. Right? This is 4x. If you can't see that, just calculate it. So now we can say what the reaction order is just with respect to NO2. as you'll see later, how we formally can calculate this, all right? If we double the concentration and the reaction rate quadruples, that's going to be a second order. It's the square, right? The rate increases by the square of the concentration change. The rate increases by the square of the concentration change. So that's going to be second order with respect to the concentration of NO2. And then overall, then our overall rate law would be the rate of this reaction is going to be equal to some proportionality constant K, which is still a mystery to you, times the concentration of NO2 squared times the concentration of CO to the 0 power. And who remembers what value do you get when you raise a number to the power of 0? You get 1. So this is the same as K times NO2 squared. That's it. Because this value is 1. And overall, this reaction is second order. So this reaction, by experiment, this reaction shows overall second order rate kinetics. And within that data, it's second order with respect to one reactant and 0 order with respect to another. That's very different from the other hypothesis, which is we double each one and the rate doubles. That would, as you'll see in the next example, well, what would you think that'd be called? If we doubled the concentration and this only doubled, what order would that be, do you think? There's only one left. First order, right? In the first order, right, the rate increases the same magnitude as the concentration changed, all right? If it's second order, it changes by the square of the concentration change. If we were considering third order, it would change by the cube, all right? So the rate would go up by a power of 3 to whatever the concentration changes. But we're not doing that. You guys give it a try. I think you can do it. Here's a new reaction. So go ahead, work with your neighbor or work with your island group. And let's come up, you do them individually. So I want to know what the reaction order is with respect to each reactant, and then write what your overall rate equation would be. Hopefully you found this one easy, but if not, it's okay. We're just learning the process. So let me take you through it. These really all work the same way. It's just recognizing what you need to do and looking for what you need in the data table. It's not always going to be presented to you in the exact same way, and it won't always be a nice 2x, 3x, 4x increase, all right? But I think for this example it is. So we're looking for the two reactants, blue, the two reactants, all right? And let's look for an experiment. I mean, you have to find two where one thing's changing and the other thing is not. So let's just look at 1 and 2. I see that between 1 and 2, this stays the same. And when I do that, and I increase and I double the concentration of, what is O3? Ozone. So when ozone, so I don't need to write when NO is constant now. Actually, let's go ahead and do that. Let's just be thorough. When NO concentration is constant, right, we're going to double the concentration of ozone. What does that do to the rate? The rate doubles. That's 2x. So that means it's which order with respect to ozone? First order. So ozone to the first, it's first order with respect to the concentration of ozone. All right, now I'll switch to red. I'm not going to do that each time. And now let's find, now look, we can't do experiment 2 and 3 because in experiment 2 and 3, both things are changing. No. If any of you did that, that's why you got confused. We need 2 experiments where only one variable changes. That's going to be between 1 and 3. And between 1 and 3, these 2 stay the same. And now the NO concentration is doubling. Okay, so when the ozone concentration is constant and we're doubling the NO concentration, what happens to the rate? It doubles. Okay, so we would write that as NO to the first power, and this is now first order with respect to NO. Now we can write our rate law because we've accounted for all of the reactants. We've done enough experiments, and hopefully you would do things. I mean, in real life, folks, you don't do this just once, right? Any kind of research, it's called research for a reason, right? You've always got to repeat your experiment. An N of 1 experiment means absolutely nothing. Even if it proves your hypothesis, you don't know anything if you've just done something once. But that's another lecture, not in this class, not coming soon to you. All right, so that means we're first order with both of them. And the overall rate law then is the rate is equal to some proportionality constant times the concentration of NO raised to the first power times the concentration of O3 raised to the first power. And those can be in either order. I realized as I was writing it that I switched the order of what they are in the equation, but that's okay. There's no convention, there's no rule for that. Okay? And this reaction then would display second order kinetics overall. And just to remind you now, the units of rate, it's always molarity per second. Always be mindful of the units. Why does it display second order kinetics overall? Excellent question. It's how we define the terms, okay? So the reaction overall is second order because it's just the sum of the individual orders. Okay. So the answer is that's how we define it.
Got it.
Want to do one more? This one looks to be about exactly the same. I'll let you do it.
What did you think I was doing? Actually.
Because these change and
All right, let's bring it in. Even if you're not completely done yet, hopefully you're most of the way there. You know, this is really good. It's a good workout, okay? We're doing this now. I mean, you've only just learned this stuff, 20 minutes ago. And here you are now working out with some problems. But these are the kinds of problems. There's lots of these in the back of the chapter. So practice, practice, practice. That's the only way to really get on top of this stuff so that if you see it on an exam, you know how to do it. You don't have to second guess yourself. Okay? All right, let's work through it. In between experiments 1 and 2, I see that the chlorine gas concentration doesn't change. So when that doesn't change, we're holding that constant. When we double the NO concentration, what's happening to the rate? It looks like it's quadrupling to me, 4x. So for this one, we can see that we are, now I don't need to write this out, hopefully for the third time. When the chlorine concentration is constant, right, when we double the NO concentration, that leads to a 4x increase in the rate. So that gives us second order with respect to the NO concentration. Yes? Good. All right, now let's look for the other one. The other one we need, now NO is constant, so that's these two. So what's the change there? Oh, looky there. It's fourfold again. All right? So, but that doesn't tell you anything yet. All that tells you is that when we increase the chlorine concentration by fourfold, what's happening to the rate? The rate's also going up fourfold. So what is the reaction order with respect to chlorine? It's first order, okay? Because don't be fooled by how much it increases by. You've got to look at what the increase in concentration is relative to how that affects the increase in the rate. That's what's actually shown down here. This is the formal mathematical interpretation of what we're doing. Okay? So it doesn't matter. It could have increased by 3.456 fold. Okay? Doesn't matter. If the rate also increased by 346, whatever I said, fold, then it's first order. Right? If it's the square of that, then it's second order. If it's the cube of that, then it's third order. That's really what this equation is showing. Okay? If you want more insight into that, then you can go and look in the textbook. I don't want to befuddle you with showing you the actual derivation of why this works, but it has to do with this starting, and then if you're given numbers that aren't easy to interpret, you actually take the log of both sides and work that through, and it all works out, okay? We don't need to go there, right? It's all in the textbook for your pleasure. You want to see the mathematical interpretation of all this. But that's all that we're doing here, okay? So, so the overall rate then is going to be some rate constant, K, proportionality constant, times the concentration of NO squared times Cl2. And you know what, folks? If there's a 1, you don't have to show it, just like with anything in chemistry. We've been showing the 1 now for emphasis, but it's perfectly correct if you don't show a 1 there. Now, if there's a 0 and you don't show it, if I showed this but it was really 0 order with Cl2, that would be wrong. Because the way I wrote this here in red, that's first order. If it's 0 order and you don't want to show the 0, then you leave this whole term out completely because that's 1. I mean, the whole thing is 1. This would be overall, this would have third order kinetics. Okay? Just one more example, but I'll run through this for you, right? Because this is like what real world data would look like. Everything that we've done so far is pre-packaged, formulated numbers so that they all come out to be perfectly 2-fold, 3-fold, 4-fold, whatever. Same thing, but now we're using some real numbers, okay? So, once again, the approach is you take a look, you find something that's not changing, and then when that doesn't change, how is this changing? What is that? Now, I can't tell by just looking at it, but I don't think it's going to be a perfect integer, so let's get our calculators out. 0.066 divided by 0.025, so that's 2.64. It increases from 1 to 2, okay? So when that happens, what happens to the rate here? You got to do it the same direction, right? It's kind of funky because you've got these really small exponents, right? Just punch it into your calculator, make sure you go the right way. We want 2 divided by 1 to give us the increase, right? So that's going to be 4.1 divided by 1.6. It's also 2.56, or not also, 2.56. Again, it's not perfect. But by the way, be careful when you do this, all right? Some of these are tricky because the exponents, one is 10 to the minus 4th and one's 10 to the minus 5th. And you got to know which one's larger than the other one and what direction you're going into, all right? So be wary of that. All right, so that's not perfect, but it's close, okay? If we punched all that in these numbers, all right, and you were asked, if you were given choices, if it's first order, second order, or third order, which one would you choose? First, okay? Even though it's not dead on first. And then the other one, here this is constant. So when that's constant, what's happening to this one? Now this one is perfectly doubling. That's 2x. And what's happening here? Looks like it's going up by 4. 3.875. So not quite 4, but if you had to guess, we can round that to 4. It's probably second order. Okay? So again, if it's real world data, of course you wouldn't do it just once. If it's real world data, you would repeat several times. But ultimately, what we're recognizing is that the concentration of NO looks like, now let's see, I just wrote all over this. Let's see, when NO doubles, we get 3.9-fold increase in the rate, right? That's approximately second order. And when we go by 2.64-fold of O2, the rate goes up by 2.56-fold. And that's approximately first order. So we would approximate this then to be the rate is equal to the proportionality constant times O2 raised to the first power times NO raised to the second power, third order overall. Now, if you want to, if you don't trust me, go ahead and plug the numbers into this. Go ahead and do it, and then calculate n. You have to know how to do the log of both sides, and then take the anti-log to figure out. You solve for n, you will get, I'll just tell you, you would get n is equal to, and I have it written here in my notes, n is equal to 1.95 for NO, and n is equal to 0.97 for O2, if you were to do it. So notice that we're doing all of this, we're ignoring the coefficients of our balanced equation. Okay? Because what did I say at the beginning? You can't tell what's going on with the rate. Right? The molar stoichiometry, the balancing, that tells you the molar ratios of how things react in their proportions. And that's what we did earlier in Gen Chem, all right? But they tell you nothing. Here, let's reinforce this. Coefficients tell you nothing about rate kinetics. Nor do they tell you anything about the mechanism. We'll get to later. Mechanism. Those have to be determined experimentally.